So today we are going to talk about what are multi-arm bandits and what is upper confidence bound and exploration and exploitation trade-off. So in the last video we saw what is reinforcement learning and what is planning. We saw the famous reinforcement learning loop and we also saw what is Markov decision process, right? We discussed what is a particular policy and how do we optimize a particular policy. We haven't seen that part yet. Okay, so we will now move on to something called multi-arm bandits. So let's take an example. Let's say you go to a casino and you are presented in front of you with a slot machine. The slot machine has a lever with it that when you pull it down gives you a reward with a particular value. Let's say you get $1 million if you hit the jackpot, right? So this is called single arm bandit. That means you have a single arm that you can pull. But in the case of multi-arm bandit, what you have is you have multiple such slot machines in front of you. So now you have here in this case, let's say k such slot machines are there and you have a k is equal to 3. So you can decide which lever to pull, and let's say with certain probability each one of these act and give you a particular reward, right? This is something we call as multi-arm bandit. So you are given that at each state you have k actions that you can take. For example, in this case you have k is equal to 3, right? And when you take a particular action, you get a particular reward corresponding to that particular action. The goal is that we want to maximize the reward. Now the difference between this particular scenario and the scenario we saw in the last video, that is for reinforcement learning, is that once you take a particular action, you return to the same state again. That means that you start with ST, then you take a particular action AT, and then you return to the same state ST, and this loop continues. So essentially you are stuck in a same state. That means the slot machines will return to the same state again and you have to take the action again. Now this is a very special case of reinforcement learning where the state space, all the states, that means all the states so far are same, right? But in the case of reinforcement learning, we saw that you have a sequence of state action next state pairs, and that have to be done till a particular episode length of finite or infinite length, right? So how do we go about optimizing it? So let's say we want to define a q value for a particular action. That means here we have 3 actions and all 3 of these slot machines are going to act differently, a little bit differently or a lot of differently from each other. So let's say we have a function q star, which is the optimal reward, expected reward that you'll get if you take an action A, right? So this is the optimal value of A. So if we know that what is the value of q star A, then it becomes very simple to decide which action to take, because then what we can do is that we can simply take argmax over A. That means we pick the best action, that is the action that gives you the maximum QA, right? But the problem is that we do not know what is the value of q star A. So we approximate using some form of sampling, right? So what is that? What does that mean? That means that you will pull the lever again and again and again, each one of these again and again, to get an estimate of what kind of rewards you get when you pull the lever, right? So that means that you will use sampling to figure out what is the value of action A till time step t, right? You have executed a particular action A or a sequence of actions A, and at particular time step A, what is the estimate or the value estimate for action A, right? And we would want q star to be very close to q, right? So now in this case what happens is that let's say you pull this particular lever, right, and you get a reward of +5. That means you get $5, right? Now it is our choice that whether we want to try new slot machines, the rest of the 2, or we continue pulling this down and get $5 each time. What may happen is that this is a dilemma. What may happen is that let's say this particular machine may end up giving us $500, right? So how do we optimize it? So we have to do a trade-off between exploration and exploitation. That means we can exploit our experiences so far, that we have learned so far, that the first slot machine gives us $5, right? But we can also try to explore and see whether other slot machines can give me better reward or not, right? So the point is, should I greedily take best action versus should I try a new action, right? So this is called exploration and exploitation trade-off. Okay. So now the question is, how do you find QTA? Okay. So the simple way to do it would be that you take the average reward that you have seen so far. Okay. So reward when A is equal to A and number of times the action A has been taken, right? Here it should be sum. Okay. And then what you can do at any time step is that you can pick the action greedily, right? The problem with this particular thing is that you always pick the same action greedily, right? So there is no exploration. So it does not even try to select any other action that may or may not lead to better reward, as we saw earlier in the exploration versus exploitation trade-off, right? So for example, let's take an example in this case. Let's say you have two actions A1 and A2. And the reward function is given in this way, that you get 100 with probability 0.1, that means you get $100 with probability 0.1, but otherwise you'll get a single dollar. And in case of A2, it is the other way around, that means you get $1 with probability 0.1, but $100 otherwise, right? So now let's say at a particular time step you took A1, that means it returned 100 with some probability. There's a 10% chance it will return 100. Then because A2 has never been taken before and A1 is now giving you $100, with this particular policy where you always pick the best action greedily, what will happen is that you will again pick A1 again and again and again without even trying A2. But in reality, A2 is a better action. Why is that? Because let's see what is the expected reward in the case of A1 and A2. So for A1, it is 100 into 0.1, right? Plus $1 into 0.99. That turns out to be $10.99, right? In the case of A2, however, you get $1 with 0.1 probability and $100 with 0.99. That's an issue because it should be 0.90, right? Apologies for that. So you'll get 99 point, right? So you'll get 99.1. Okay. So now clearly this particular reward is far greater than this particular reward. So ideally you should have picked A2 more often, but what happens is that because you are picking things greedily, you will end up choosing A1 all the time. Okay. So what is the solution with that? The most easiest solution would be to try something called Epsilon greedy policy. That means with some random probability, very small probability, you will take a random action and otherwise you will pick a greedy action, right? So that's what it is saying, that with epsilon probability, take a action uniform randomly or otherwise you take greedy. Now the benefit of this is that in this scenario, if you have taken A1 it had given you 100 reward in the first step, in the next step with some very small probability, you will still try A2 independently of what is the reward of A1, right? So theoretically speaking, as time approaches infinity, all actions will be taken infinitely number of times. Hence, as time approaches infinity, Qt will approach Q star. There is a theoretical proof for that and we will not go into that. Okay. So now to have a coding solution for this, what we can do is that we can keep track of all the rewards we have gotten for each of these slot machines so far. For example, let's say in the first case you got plus $5, then you got $5 again, then you got 0, 0, 0 and so forth. And let's say in the second case you get, let's say a point plus $100, then $5, then $20 and so on and so forth. And in the third case, let's say you get $500 and $100 and then you get $0 or $0 and so on and so forth. So to write a code of this, we have to maintain a list for each of them, and at every time we want to find the policy, we have to take the average of the rewards independently for all of these and then decide which one is better, right? But it's not a good solution. How do we go about keeping a running average of this? So what we want is that we want our r1 plus r tilde point t divided by t, right? So we can break, and at time t plus 1 we will like to have this particular computation. So now in this case we have to add these numbers again, which we had already added in the previous time step. So can we leverage it? Okay, so what we can do is that we can represent this as this particular thing as, if we take the t to the left hand side, you get qt into qta into t, right? So here if we leave it here, that essentially means that you multiply the previous reward, the previous q value at time step t with t, and you add the current return that you got, reward that you got, and divide it by t plus 1. So this has one multiplication, one addition, and one division, right? So can we simplify it further, right? So what we will do is that we will add and subtract qt plus a in this case. So it becomes t plus 1 qta, it becomes qta plus rt1. Now if we shuffle these problems a little bit, take the t plus 1 inside the brackets here, you get qt plus 1 and the reward you got at t plus 1 minus qta divided by t plus 1. So this has one subtraction, one addition, and one division. That's it. So this is better than this particular formulation, while you can still use this. Why? Because this has one multiplication, and this multiplication is being replaced by a subtraction, right? So you can think of it as the famous deep learning based update rule, that where you have an old estimate plus step size into error in the estimation, right? So if this is the actual value, then and you get this particular reward, then what is the difference between these two? That is the error in the estimation, and then you update it. Okay, this sounds very familiar to the learning rate update for SGT and all, right? Okay, so next we will see that can we do something better than epsilon greedy. Okay, because epsilon greedy is fine and all, but can we do better? So what is our goal? What do we want? We want to do an exploration, and it should be based on the potential of an action to become optimal. Okay, so if you have, let's say, 5 action with you, a1, a2, and a5, and this is the rewards that you get in each one of these, let's say, and you get, let's say, even lower in a3. Okay, so now what happens is that this is the greedy action, a1 is the greedy action, but when epsilon greedy, what we will do is that with epsilon probability, that is very small probability, we will uniformly randomly pick any of these particular these actions. But we would want that if we are not going to take a1, we would like to take a2 more than we would like to take a3, right? Provided that estimates of a2 and a3 have stabilized. So now can we do it automatically or not, right? So what should our action depend on? It should depend on the value estimate and the uncertainty in the estimate that we have formulated so far, right? So we would like to select action at based on argmax of some function. That function should be based on the current q value of that action and some measure of uncertainty of the value. How do we measure the uncertainty? This is very simple. Okay, so we take we have two terms, where the second term is a multiplication of c, which is a constant that guides how much value you want to put on the measure of uncertainty as compared to the q, actual value of the value of the action. And in the numerator we have log of time, and then denominator we have the number of times a particular action has been taken before the time t. Yeah. Now let's see what happens in various conditions. So if NA increases, that means number of times you have pulled a particular slot machine increases. Okay, so then this particular value will decrease, right? So if you have already tried a particular slot machine multiple number of times, then you would not want to try it again and again. So this particular value decreases, so the overall value goes down, right? Now now if NA is equal to 0, if NA is equal to 0, A is the maximizing action. That means if you have never tried a particular slot machines, you should always try it, because 1 by 0 will be equal to infinity, right? If A is not selected, NA remains same. If you have 5 actions like we had, right? So if we pick an action that is not pick an action, rest of the 4 actions will not be selected. For those cases, the time will increase, but number of times the action was selected will remain constant. That means that if you do not pick an action for a very long period of time, let's say you keep on ignoring the action A3 for a very long period of time, you always pick A1, A2, A4 and A5, then the time thing will keep on increasing, but this particular value will not increase, hence this overall value will continue to increase. So resulting in this particular value completely increasing over and over again and again, right? So this is a very good metric. This is a very good formulation to balance the value of a particular action and the uncertainty in that particular action's value estimation. Okay, so this is known as upper confidence bound. So that's all for this particular video. We will move on to Monte Carlo tree search next in the following video. Thanks for watching.